The observations indicate that one jet, the eastern jet, is moving along a line tilted towards the Earth, whereas the western jet is pointed away from the Earth. This alignment explains why the eastern jet appears to have traveled further from the black hole than the western one. However, with this alignment, the eastern jet should be brighter than the western one, while the western jet was actually 3 times brighter. The CHANDRA researchers are not aware that the brighter, more distant jet can be explained by their own data. The X-ray photographs gives a distance measure for the first appearance of the closer, dimmer jet, and another distance measure for its disappearance just as the brighter jet appears. Using quantum dimensional open energy equations, we find that the energy given by the black hole to the dimmer jet when it first appears is nearly eliminated as the jet fades. The black hole has lost its capacity to provide energy to the jet materials. The brighter, further jet appears exactly at the time the black hole has lost its capacity to contribute energy to the jet's radiation emissions. The loss of the black hole's capacity to add energy to both jets is the significant factor. The further, brighter jet is obviously of heavier material. Throughout the process of the black hole's gravitational contribution to jet heat, the amount of energy contributed is greater for the more massive western jet than it is for the lighter eastern jet. The lighter eastern jet is likely composed of hydrogen, which cannot store energy and will cool by radiation in direct relationship to the energy it receives from the black hole gravity. The greater energy provided the heavier western jet results in both more energetic radiation emissions and slower cooling. It is only when the black hole has ceased providing energy that the western jet's radiation cooling can eliminate stored energy. This occurs exactly when the lighter jet fades, having been shown mathematically to have lost 98% of black hole energy contribution. The jet disappears when the black hole is no longer contributing energy. The appearance of the brighter, higher energy jet at the disappearance of the lower energy jet tells us what is happening. The brighter jet can only become visible after the black hole has ceased contributing energy. However, the claim that the CHANDRA data explains the mysterious brighter, further jet versus the dimmer, nearer jet is made credible only by the gravitational open energy equation. If those mathematics are not credible, then neither is the explanation. The subject for the remainder of this lecture will be mathematics. Knowledge of basic gravitational mechanics and basic calculus will be required. We begin our examination of the quantum dimensional extension of gravitational mathematics with Newton. In 1679, Isaac Newton and Robert Hooke began a thought experiment of what would happen if something fell from the surface of the Earth to the center. This is reported in Newton's notebook. Newton developed his famous elliptical orbit formulation for this thought experiment, which can be seen in his own handwritten illustration. The problem is that the Hooke-Newton thought experiment didn't reflect actual reality. They converted the mass of the Earth to space and made the center of the Earth stand for the Earth's mass. That is, they geometrically converted the three-dimensional space which actually defines mass into a two-dimensional plane and mass into a point within that plane. The result of this geometric conversion was the discovery of the famous elliptical orbit and the gravitational closed energy system. But what would happen if we didn't follow Newton in this geometric conversion? What would happen if we drilled a hole to the center of the Earth and dropped something in it, describing the gravitational influences of the fall in the hole to the center of the Earth? What we would find is a whole set of gravitational influences quite different from those proposed by the original Newton thought experiment. We can agree with Newton that the velocity of spin for an object at the surface of the Earth is greater than the velocity of spin for points closer to the center. For this reason, any object dropped into the hole from the surface will bounce on the walls of the hole as it drops towards the center. Our issue, however, is what happens to gravitational acceleration as the object drops further down the hole. The gravitational influence of a mass is the acceleration rate it produces on a smaller mass. The gravitational acceleration rate at the surface of the Earth is approximately 9.8 meters per second squared. The rate will become less than this as the object falls toward the center. The acceleration rate will become zero at the center. This is a surety because the object is pulled downward by decreasing mass ahead of its motion, while the mass which it has passed in the hole and is now behind will provide a counter-gravitational influence. This counter-influence reduces gravitational acceleration rates, which will reach zero at the center of the Earth, as the mass influence ahead and the mass influence behind have become equal. What this means is that the original Newton thought experiment was inadequate because the rate of gravitational influence above the surface is not equivalent with the rate of influence below the surface. The rate of above the surface is determined by the standard gravitational equation as shown on the blackboard. Above the surface, the gravitational forces expressed by the rate of acceleration of the falling object is increased as the distance to the center becomes less. As r becomes smaller, acceleration increases. As we have demonstrated, when a falling object falls below the surface within the mass, the relationship between the distance and acceleration reverses itself. Below the surface and within the mass, the rate of acceleration decreases as the object approaches the center of the Earth. Above the surface, the rate of acceleration increases as the object approaches the center of the Earth. Gravity does not operate the same outside versus within an attracting mass. For this reason, to make the gravitational equation accurate, we must set the radius of the attracting mass equal to a quantum. The maximum acceleration will be at the surface of the Earth. Since we have set the radius of the Earth equal to the quantum, maximum acceleration is equal to the mass divided by 1 squared. This is our constant acceleration g at the surface of the Earth. We now have a value for mass based upon maximum acceleration. That is, mass m2 is equal to g times 1 squared. This converts the mass value to the acceleration constant g. The maximum surface acceleration rate can now be substituted for the mass of the Earth in the common acceleration equation. This is only true if we measure the distance x in quantum radial units. That is, the radius of the Earth has become our unit of measure for any distance. This discovery that the surface of a mass provides maximum acceleration, which can be substituted for the value mass in a quantum gravitational equation, allows us to describe gravity as an open energy system. But this is only true for bodies coming from completely outside the gravitational system and captured by it. The object undergoing energy creation through the gravity open energy system must come from outside the gravitational system. Is this even possible? Actually, it is quite common. Small rocks in approximate solar orbit to us are captured by the Earth's gravitational system and flash across our skies as meteorites. This occurs when the force of the Earth's gravity upon the object becomes greater than the force of the Sun's gravity. In this case, the Earth's gravity captures the object which has entered our system from outside. The meteor is accelerated by the Earth's gravity, gaining energy which is most often converted to friction heat against our atmosphere. What conventional physics fails to recognize about these meteorites is that they have not brought this energy expended upon our atmosphere with them, but that it has been largely created by the Earth's gravitational system. Physics cannot recognize it because the possibility appears to violate the law of the conservation of energy, of the first law of thermodynamics. They do not realize that this law applies only to closed energy systems, not to open energy systems. They cannot recognize the distinction because they have no mathematics for the open energy systems. It is that missing set of mathematics which we are about to present. The problem for conventional physics is they cannot integrate the gravitational equation across the fall, and such an integration is required to find the average acceleration across the distance of fall. The average is needed to find the energy gain. This integral is simply not possible using conventional physics and conventional calculus. But look what happens when we use the quantum mathematics for the gravitational equation. The derivative of the quantum negation of subdivision, that is 1 minus the subdivision, is equal to the needed gravitational equation. 1 minus the subdivision times the gravitational constant is equal to the gravitational equation. This allows us to integrate between 1, or the gravitational value at the surface of the Earth, and the point x at which the object enters the gravitational system. By quantum calculus, we are no longer required to integrate from r equals 0, but from x equals 1. Since the integration of the derivative is equal to the equality, we now have an exact value for the average acceleration across the distance of fall equal to 1 minus 1 over x times the gravitational constant acceleration at the surface of the Earth, which we have designated as g. I realize we have covered these mathematics too rapidly, but a more detailed version is contained in the text accompanying the lecture. The title of that text is, quote, Gravity Open Energy PDF. We have established that gravity can create energy for a falling object which has entered the system from outside. We must now return to the black hole. The CHANDRA black hole operates in the opposite direction as an object entering a gravitational system from above and falling to the surface. The black hole jet matter is accelerated across the rift in quantum space to enter the black hole gravitational system from below at the radial distance of the rift. The formula for jet change in velocity entering the surface of the system from the surface of the system is different than the formula for change in velocity of objects entering the gravitational system from above. That formula is velocity equals the jet's initial velocity of the speed of light minus the change in velocity due to the black hole gravity as calculated by the quantum energy formula. That formula is x minus 1 times the square root of 2 times the gravitational constant divided by x. You might recognize in this square root factor a factor very similar to that which is used to calculate escape velocities in standard gravitational systems. We can demonstrate by this equality how the energy contribution from black hole gravity changes as a jet moves further from the rift. This is explained on page 14 of the text for this course, which I will quote to end this lecture. What can quantum dimensional calculus tell us about the observed performances of Chandra's J1550-564 black hole jet? The change in velocity and the greatest conversion to heat will occur within the first black hole radial distance after the matter re-enters quantum space. By the open energy equation, velocity will change by the square root of the gravitational constant, and the amount of kinetic energy exchanged for heat energy will equal mass times 1/2 the gravitational constant. For the next radial distance of travel, velocity will change by 0.663 of the square root of the gravitational constant, and the kinetic to heat energy exchange will equal mass times only 20% of the gravitational constant. By the second radial distance of travel, energy exchange will be less than 1/2 that exchange during the first radial distance of travel.